Hey guys, welcome to your next tutorial. Today's tutorial is going to be mainly conceptual. It's going to be more of a computer science tutorial, and we're going to talk about what the cache is, why you should care about it, and how to use it to make your programs a lot more efficient. Now, I've probably talked about this a little bit in some of my previous tutorials, but I haven't devoted a whole tutorial to it, so this is going to be very informative, hopefully. Alright, so take a look at this little diagram that I ripped off the internet. At the top we have the CPU. This is your central processing unit, of course. This is where all your code runs. This is, the brain of your computer pretty much. And then we have at the bottom here, we have RAM. This is your random access memory. This is where all your variables are stored on the heap and all that. And then in the middle, we have the cache. So this cache was invented to speed up the access of your variables and all that stuff in RAM, because whenever you want to go and access something in RAM, it's actually really, really slow. Now, compared to accessing something on your hard disk, it's fast, but it's still not quick. And if our CPU is constantly having to wait for data to return from RAM once we're, making requests, then it's going to slow down our program a lot. So what you can think of the cache is it's like a small version of RAM. It's a very small little memory buffer that holds things from RAM so that we can access them quicker. The cache actually consists of 3 levels usually. You have an L1, an L2, and an L3. The L1 is the smallest, L3 is the biggest, and the L1 is the closest to the CPU. Now, whenever you want to access the cache, it's way, way faster than accessing RAM because the cache is smaller and it's built really close to the CPU. Now, here is how an access works if you want to actually look something up. So let's say we're on our CPU, our program's running, and we just started our program, so our cache is probably empty, and we want to ask for the variable a, which is a heap allocated variable. So the first thing we're going to do is we're going to look in the cache for the data. So we're going to come along here, we're going to be like, okay, is the variable a in the cache? And no, it's not, because our program just ran. Okay, whatever. Then we're going to come down here and fetch it from RAM since it's not in the cache. This is really slow, unfortunately. We're going to grab the variable, and it's going to come back up this pipe here, and it's going to get written to the cache. So it's going to take that variable and write it to the cache. But it's not just going to write that one variable. It's actually going to write an entire cache line, which is typically 64 bytes. So even if your variable a is 8 bytes, once it comes down here to RAM, it's going to grab a, and it's going to grab all the 64 bytes around a, and bring them back. And it's going to write all 64 of those to the cache. And then it's going to return you just a back up to the CPU. Now, why did it grab 64 bytes? Why didn't it just grab a? Well, the reason is typically whenever you're accessing data on the CPU, you're going to be accessing a lot of the data that's kind of local in memory or in contiguous memory. For instance, let's say a is an array, and we wanted to access the very first element of a. Well, as you know, arrays are allocated contiguously in memory, meaning the first element of A is right next to the second element, which is right next to the third element. So if we're doing something like iterating through an array, what's going to happen is those 64 bytes that are in the cache are going to keep getting reused. Let's say A is an array of chars, so it's an array of bytes. If we ask for the first byte, it's going to grab the first element and all the way through the 64th element. It's going to grab all of those and put them in the cache. So now we're on the CPU and we're iterating through A, and we're going to increase our I counter or whatever, and now we're looking for the second element of A, or A0, or A1, sorry. So what we're going to do is we're going to look for in the cache for A1, and surprise, it's there because we grabbed 64 bytes from RAM, including the second element of A. And we're going to come back, which is much faster than before since we don't have to go to RAM. Then we're going to go to the third element, and it's in the cache, and this is going to repeat. Each time we come and iterate through an element, it's going to be in the cache, all the way until we get to the 65th element. And finally, since we only grabbed 64 bytes, it's not going to be in the cache, so we're going to have to come down here and grab it from RAM again, and the process repeats. Now that's incredibly, incredibly faster than if we didn't have a cache, because we would have to constantly be grabbing things from RAM. If that confused you, let's go to a little simpler example, sort of a real-world analogy. I drew this crappy little thing. This is the Librarian Analogy. I don't remember where I got it from, but it's a really good one. So this little red guy over here, this is you, this is the CPU. He wants to get things from memory or whatever. You can think of him as trying to check out a book from the library. We can say a variable is a book. or a block of memory is a book. And this blue thing right here, this blue guy, this is the librarian. You can think of it as the bus on the computer that is going to be accessing all the data. So let's say your little red guy here wants the first Harry Potter book. So the blue guy is going to have to, come over here and march all the way down here and grab Harry Potter. So let's grab Harry Potter. We'll grab it. And then he's got to walk all the way back. Oops. He's got to walk all the way back and put the book in your hand. And that was, that took a while. He had to walk all the way back here. Now, our little example here is unique. It's not really a real-world example because your red guy can only ask for one book at a time, which in real life you probably wouldn't be doing that, but that's what happens in our example here. So you wanted the first Harry Potter book, but you're actually going to want to read all the Harry Potter books. So now you have to ask for the second Harry Potter book. So the librarian's like, oh crap, I got to walk all the way back and get the second Harry Potter book. So he walks all the way back, he grabs the second one, and you can see how this process could repeat for a really long time. Let's say you want the whole Harry Potter series. He's going to have to keep walking back and forth, and it just sucks. So let's not do that. That's not good. Instead, let's give our librarian a cart. So we'll give him a little cart, a little brown cart here, and we'll give it some wheels because, it's important to pay attention to art in these situations. All right, so here's our little cart. Now the cart is the cache. Now, whenever your guy here asks for Harry Potter Volume 1, what's going to happen is our librarian's going to bring the cart with him over here. And instead of grabbing just Harry Potter Volume 1, he's going to be like, well, he might actually want the other Harry Potter books, or maybe some other books that have similar titles. So he's going to grab a whole cache line. He's going to grab all these books and put them in here. Then he's going to wheel them all the way back. And he's going to give Harry Potter Volume 1 to our little red guy. And the red guy is going to be happy with Volume 1, but he wants Volume 2, just as the librarian anticipated. So now the librarian, instead of having to walk all the way back to the bookshelf, he can just grab Volume 2 out of the cart. And this will repeat until either the red guy asks for a book that isn't in the cart, or the cart is empty. Which actually, whenever you pull books out of the cache, it doesn't become empty. You just copy them out, so that won't happen. But you get the idea. So that is a conceptual overview of the cache. If you want a more technical overview of it, just Google it. There's tons of information about the cache that you guys can read about, like the size of the cache. I don't remember exactly how big each cache is, but you can look up that. And you can look up the exact memory access times for cache. Real quick, I'll show you a real-world example of what is cache-friendly and what is not cache-friendly. So let's go to graphics tutorials here. Let's say we are doing polymorphism. This is actually going to be directly relevant to our next tutorial. Let's say we have a class A. All right, and class A has just one protected variable, int A, or something like that. And then we have a class B. All right, and B has a protected variable B, or whatever. These variables don't really even matter. Now B is going to inherit from A, so we'll say public A. And let's use some polymorphism. Let's say we want to have an array of A pointers, and we want to make them all of type B. So we're going to have A, we'll make it a dynamic array. So we're going to say A star array or something. Or we'll say my array. Give it a dumb name. And let's go ahead and allocate it. So this is the cache-friendly way to do it. What we could do is we could say my array equals new B, we'll say like 1,000 Bs or something like that. Now this is going to be cache-friendly. When we go to iterate B, this is going to be a contiguous array. So when we loop through all these elements, they're going to get loaded into cache because they're all right next to each other in RAM. So remember, this is how arrays work. They're contiguous. However, if we did something like this, where instead of doing an A star my array and making a dynamic array of B, if we instead use like a vector, we'll say std vector, and we'll make it a vector of A stars, so we can do polymorphism, myvec. If we instead said myvec.resize 1,000, now remember, resize isn't going to allocate the pointers memory, it's just going to allocate the pointers themselves. Now we need to loop through for int I equals 0, I is less than myvec.size, I plus plus. And we would say myvec I equals new b. There we go. So this is going to be not cache friendly. Now, in both cases, you're going to end up with sort of an array of b in a polymorphic way. However, in this case, we're calling new a bunch of times. Now, that whenever you're calling new a bunch of times, you can know something's probably amiss, and this probably isn't going to be cache friendly. In our previous example, we called new one time that allocated one contiguous block of memory. It was great. In this, we're calling new a bunch of times, and each time we call new, the memory might be contiguous. It might be allocated right next to the previous one, but typically it's going to be kind of scattered around. So whenever the cache goes to grab the memory around, say, myvec 0, it may not contain the memory from myvec 1. So this is the slow way to do it. This is not how you want to do it. You want to, whenever you can, if at all possible, you want to make sure that your memory is in contiguous buffers like this. Or, just if you weren't doing polymorphism, you would want to make sure it was, just a contiguous array like that. So thanks for watching this tutorial. I hope this made sense. There's plenty of resources online if you want to go more in depth with the cache. We're going to be using this in our next tutorial to make sure that our particle engine is really efficient. Thanks for watching, guys.